Today, we're diving into one of the most fundamental rules of the quantum world. It's a rule that explains everything from why your desk is solid to how massive stars avoid collapsing on themselves. We're talking about Fermi-Dirac statistics, but let's just think of it as the universe's ultimate seating chart. All right, to get into this, let's go back in time to the 1920s. Physicists were studying metals, and they ran into a really weird problem. I mean, on the one hand, metals conduct electricity like champs, which made total sense. But on the other, they acted so bizarrely when you tried to heat them up. And here's the heart of that mystery. To carry a strong electric current, you need a ton of electrons, a whole sea of them, all free to move around. But when scientists measured how much heat a metal could actually store, what we call its heat capacity, the numbers suggested that only a tiny fraction of those electrons, something like 100 times fewer, were even involved. So how could almost all the electrons carry a current, but almost none of them absorb any heat? Classical physics just had no clue. Well, the solution to this paradox wasn't some small tweak to the old theories. Nope, it demanded a completely new understanding of matter. And it all comes down to a group of particles that are, well, you could say they're profoundly antisocial. So to solve this whole metal mystery, first we've got to meet these particles and learn the really strict rules they're forced to live by. Our main characters are called fermions. Now, this family includes the basic building blocks of matter that we all know: electrons, protons, and neutrons. They have this quantum property called spin. But here's the crucial part. All identical fermions, like every single electron in the universe, are absolutely, perfectly indistinguishable from one another. You can't tell them apart. And because they're completely indistinguishable, they have to follow a non-negotiable law, one of the most important rules in all of physics, the Pauli exclusion principle. It's simple, but it's powerful. No two identical fermions can ever share the same quantum state at the same time. And this right here is the heart of our seating chart idea. Imagine the universe is just this giant auditorium with a practically infinite number of seats, and each seat is a unique quantum state. For fermions, the rule is brutally strict: one particle per seat. That's it. No exceptions. They can't share, they can't sit on each other's laps. They are fundamentally deeply antisocial. So let's connect the dots. How does this simple one per seat rule actually explain the weird behavior of metals we were talking about? Okay, so picture how the seats get filled. Electrons are, kind of lazy. They always want to be in the lowest energy state possible. So the first one comes in and grabs the best seat. The second one takes the next best empty seat, and so on and so on. They just stack up from the bottom, filling level after level, creating this vast, deep pool of occupied states that we call the Fermi sea. Now here's the crucial point. Think about an electron deep down inside that sea. All the seats immediately around it, above it, below it, they're already taken by other electrons. It has literally nowhere to go. It is effectively locked in place, pinned down by that strict Pauli exclusion principle. All right, so if they're all stuck in their seats, what happens when we try to give them some energy? Like when we heat up the metal? Well, for an electron to absorb heat, it has to get enough energy to jump up to a higher energy seat. But for all those electrons buried deep in the Fermi sea, this is impossible. Why? Because all the nearby higher energy seats are already full. It's only the electrons right at the surface of the sea, at what we call the Fermi energy, that have empty available seats right above them. They are the only ones who can actually absorb that little bit of heat and make the jump. And there you have it. The puzzle is solved. Only a tiny fraction of electrons, those ones right at the top of the sea, can absorb heat. That perfectly explains the weirdly low heat capacity. But for an electric current, that's different. You just need to give the entire sea of electrons a tiny collective nudge in one direction. They can all shift together, and that group movement is the current. So you see, all the electrons can participate in the current, but only a precious few can participate in storing heat. And this isn't just some clever answer to an old physics puzzle. Oh no, this one simple rule, one fermion per state, has consequences that literally shape the universe. I mean, almost immediately after Fermi and Dirac developed the idea in 1926, it was used by Ralph Fowler to explain how white dwarf stars, these incredibly dense, dead stars, don't collapse under their own immense gravity. Just a year later, Arnold Sommerfeld used it to finally explain metals. And today, it's absolutely essential for designing the semiconductors that power, well, everything. So the takeaway here is massive. This principle is why electrons stack up in neat orbitals, giving atoms their structure and stopping them from just collapsing into a point. It is the reason matter is stable and that you can't just walk through a wall. It generates this powerful outward pressure that holds up dead stars against gravity. And yep, it's what makes your smartphone work. All of that from one simple antisocial rule.
Now, to really get the full picture, it's important to know that these antisocial fermions aren't the only type of particle in the universe. There's a whole other family with a completely different personality. Let's just look at this comparison. We've got our antisocial fermions governed by Fermi-Dirac statistics with their super strict 1 per state rule. Then you have their counterparts, bosons. These are particles like photons, the particles of light. They're governed by Bose-Einstein statistics, and they are incredibly social. They love to crowd into the exact same state. There's no limit at all. And finally, you have the old classical idea, Maxwell-Boltzmann statistics, which just treated particles like they were tiny, distinguishable billiard balls that didn't care one bit about sharing.
It's really just a reminder that from the tiniest transistors inside our phones to the biggest stars in the sky, this concept isn't some historical footnote. It remains a vital, active part of how we understand and manipulate the world around us.
And that brings us to the end. The fact that a simple rule about seating arrangements can explain the very solidity of matter and the stability of stars, it really makes you wonder, doesn't it? What other profound, invisible rules are out there, quietly shaping the reality we experience every single day?